last session. So we have had the wonderful 2 days already. This is our last session. We usually say best for the last. So our first speaker for this afternoon session is Professor Yazhen Wang from the Statistics Department at University of Wisconsin, Madison. And Yazhen was also Peter's student. So, but I don't know your number, along the student list. Yeah, and Yazhen is also currently the department chair at the University of Wisconsin at Madison. So Yazhen, floor is yours. Thank you.
Well, thanks, Hai-Yan, for the introduction. According to the student Peter listed on his web page, I'm the number 39. And so that's the sources. I know there's some kind of ambiguity or the missing data, but my source is from the Peter's web page. So I'd like to thank Peter for the many years of inspiration and help and support and to my career. And thanks, Peter. Happy birthday. Okay. And I also like to thank the organizer for putting together this conference and for inviting me for this opportunity to give a talk. And another things I like to thank is the Simon Institute. And they organize, the institute organized many quantum computing programs over the year. I participated many in person before the pandemic, and even more during the pandemic through the Zoom. And I feel it's kind of one of the benefits, maybe for the COVID, I can kind of more freely to attend those quantum computing programs. So I will, for today's audience, I feel is for the statistics audience. And I know there's a barrier about the quantum computation and the concept. I will try to use minimal introduction of quantum computations to illustrate my point. I will keep like my talk at a high level for the simple cases, so that we can better understand the things from the statistics aspect. Now, what's the first I talk about the quantum advantage or the quantum supremacies. The way we think of when you compare quantum computational device, usually you do a theoretical proof, okay, down the theory. Another one is to build up a device for the experimental demonstration, okay. Now for quantum cases, over the years, there's a lot of the theoretical study proposing quantum algorithms, and actually you can prove there are many quantum algorithms which can be much faster than the classical algorithms, like well-known, for example, short factoring large numbers, and the algorithms which has been proven to be exponentially fast than the best known classical algorithm. Okay. Also, the group search algorithms, which has been shown is quadratically fast to the best proved classical algorithms. And actually, the quadratic fast is the optimal. And so basically, it has been optimal in the quantum sense, optimal in the classical sense, and you can compare to still have a quadratic speed up. Now we have all of those theories, method, algorithm proved based on the quantum theory. Now, well, can we demonstrate that one? So we needed to build up a device, try to run these algorithms to actually see what happened and there. So in principle, we could do is try to build up a device, try to compete against the best supercomputer and to see what happened there. Okay. Now, unfortunately, because of the technology difficulty, what we can create are the quantum computers in much smaller scale, and which cannot run those kind of the theoretically proving algorithms and to show those quantum advantage. So the way is, can we, based on what we have, do something compete with the best the supercomputer, which is similar to we show the abacus against the laptop, and you try to find out some algorithms, some computational problems to run on both to see what happened. Okay. Now, for the cases, quantum computing cases against the best supercomputer, it's basically pretty much the same as this comparison. It's just to try to find out suitable problems to demonstrate some of the things. And you may heard about the recent landmark project demonstrating quantum supremacies, basically saying take 200 seconds computational job for the quantum computer, and that one would take 10,000 years or 0.6 billion years for the best supercomputer at that time, and you finish the 200 second job, and the quantum computer did. So the two projects, one is the Google and published in Nature. It basically they find out so-called random quantum circuits. What's that one? It is a statistical sampling problem, which I will illustrate in a moment. And basically show that one at that time, the best quantum computer, best classical supercomputer would take 10,000 years. And the second project is published in the Science 2020 by USTC China, and project the build up another quantum computer, and again statistical sampling problems is called boson sampling, and they showed for that problem it would take the computational problem, it would take the best supercomputer at that time to take maybe the 0.6 billion years to finish that job. So what I will illustrate in my talk is trying to explain the statistics and associated with those projects. Now, I have to say that one is when I refer to classical computer, okay, and it means what we are currently using electronic based, okay. And the second one I like to say that one is, although we call quantum computer like a classical computer, both a computer, and you may not believing that the difference between the quantum computer and the current classical computer is much bigger than these two, like the laptops and acrobats, because of the function underlying mechanism. Okay. So let's go down to the bottom and to see what's the quantum computing. It's basically like a classical computer. It's all started with bits, like 0 and 1. And in the quantum cases, we have quantum bit, and we call it qubit. And it's also 0 and 1. We use this these kind of like notations to say it in the quantum bit. Okay. Now, unlike it in the classical cases, you only have these 2 points. Quantum theory allow us qubit in the superposition state. It's basically you have 0 and 1. Any linear combination of these is also a state, and so those two coefficients are amplitude. They have this kind of unit norm constraints. Okay, and in the moment you would see this will have the probabilistic and consequence for the random nature of the quantum qubit theory. Now, if you from these superpositions, you can see if you identify those two are the base, okay? So any linear combinations of this one superposition state corresponding a point in the two-dimensional space, okay? So the superpositions is corresponding all of those sphere on the point, every point corresponding to a state. Unlike the classical cases, they only got 2 points. Is in the classical cases, it's either on or off, like a coin, like a pro and the cons. Okay. Now in the quantum cases, you can think about it a coin which have all the state from the pro and the con, anything continuous and all of this one. So you would see it's a much bigger space. Okay. Now because of superpositions, you can think of interpret that one is in the classical cases, either head or tail, okay? And in the quantum cases, you can have both head and tail, both 0 and 1 cases continue, it's simultaneously. Now, in the classical cases, we know it is 0 and 1. And you know which state is you always easy to check. Now, in the quantum cases, you cannot directly examine the qubit to find out those coefficients, but there is you can measure the qubit, and then there's a stochastic random outcome here. So what happens is if you make any measurement of the qubit, what you will see, it will be collapsed to the 2 points, either 0 and 1 in the random cases. Now, what's the probability of observed to 0 is the corresponding coefficient amplitude modulus square. Okay, and with 1 is for this coefficient modulus square. So that's the constraint of equal to 1 allow these probability interpretations. That's where the probability comes into play in the quantum in the qubit cases. So remember that one is anything you have a qubit. You want it will, if you wanted to do measurements and get a result like digits, and then there's a probability there. Okay, you can think about the probability distribution. And because of this one, all the quantum computations, algorithms, and things are random algorithms, and there's a distribution associated with that one. Okay. Now moving to the multiple qubits. Okay, and in the 2 qubit cases, you will see there will be 4 of them. 0, 0, 0, 1, 1, 0, 0, 1, 1. Okay, so that any superposition will be linear combination of those 4. So if you think about those other bases, it occurs the space you need to handle the 2 qubit, it will be 4 dimensions. If you have 3 qubits, 8 dimensions. So if you have a b qubit, it will be 2 to the power of b dimension. You can see the exponential scale up. Okay, the superposition exponential scale up. So that's the qubit. Now, similar to the classical computer cases, we need to build up gate circuits to make the computation moving. So in the quantum cases, you can also build up the gates. And like, for example, you can change the 0 to 1, 1 to 0. Okay, but remember, we have a superposition. Okay, so the quantum theory is saying that all the qubit gates must be unitary. The transformation must be unitary. Any of this one, unlike the classical case, it must be unitary. And that one is represented by a unitary matrix. Okay, so any of these you will see compared with this one, you transform the state, and then any superposition will have the similar transformations. These are unitary matrix. So if you think about a gate, is a unitary matrix. Okay. Now the circuits, quantum circuit, is just connecting a sequence of gates together, quantum gates together. Okay, so that one is this circuit is kind of a performing. If you carry out this circuit and do a bunch of those unitary transformations, you are performing the certain computational task, and that task. Basically, if you can think about all those connected, each of the gate have a unitary matrix, you multiply together. So you will have a big unitary matrix for these circuits. So in the end, you will see whenever we talk about the circuits, you can think about a unitary matrix, big unitary matrix corresponding to that one. Okay, and so this is the computation. Now, what's the exciting? Here is just some picture to illustrate the qubit here, and you can apply the gates, and you can 1 or 2 gates, and if you carry all of them, it corresponding to a quantum circuit. Now, what's the exciting about the quantum computation is the possible speed up or fast algorithm to performing certain computational tasks, which is due to the many quantum property, which in the classical cases we don't have, like superpositions, entanglements, and so on and so forth. So if you have any algorithms on the build up on the circuits carry out that one, you have an end result automation. Everything is random. Okay, so it's basically it's like the MC algorithms. You run once, it may give you the correct or incorrect solution. Okay, but there is certain probabilities you will get the correct solution. Okay, so you repeat, you will eventually get the correct solutions. So that any algorithms corresponding end result will have a probability, the random outcome solutions, they will have a distribution associated with that one. Okay. Now, when we say that compare the classical computer and the quantum computer, you will see what's the against these two. It's basically that you're using the classical computer to solve a computational problem. If the problem is the same, you just use a different device to solve the same problem. Okay. Now the classical computer can only run the classical algorithm. Quantum computer can need to run the quantum algorithm. Now the speed up, the mentioned is the interesting about these things is the potential quantum speed up. There are many theoretically proven quantum algorithms which have the speed up over the classical algorithm. And I wanted to put that one, not always, as a matter of fact, and the many cases quantum computer don't have the speed up. It's just that for certain problems, it may have the quantum speed up. Now, again, what's the issue here? Is because we don't have the large scale quantum computer to run those theoretically proven algorithms which we can demonstrate the quantum advantage and in the practice. What we have is currently we can build up a relatively much smaller quantum computer, and which may not be imperfect. And we refer to near-term quantum computer. We still wanted to find out some problems which we will be using like the performing on the quantum computer against the best supercomputer to solve that kind of problems, trying to show there's a quantum advantage. So this is the kind of we'll refer to quantum supremacy. Okay. Now the two projects that mentioned early on are the one is the Google, another one is the USTC projects. And the Google, they build up a quantum computer is based on the superconducting qubits with 53 qubits at that time. And the design problems is referred to the random quantum circuits, and it's statistical sampling problems. And they run on this device and to solve that problems. And you will see, in a moment, I will explain what's the random quantum circuits. And the USTC is based on the quantum optic systems, photons, and build up is in the 2020s, and they also solved sampling problems. And I will explain this one. What's the boson sampling problem? They are both statistical problems to solve on that one. Now, why they choose sampling problems? As mentioned that one, that because of a limitation, the quantum computer so far we have is relatively small, and it's noisy. And so we needed to find out the problems are very suitable for those devices, okay, to perform. But on the other hand, we wanted to use that problem. It's very hard for the supercomputer, okay, to solve. So we can demonstrate advantage. So there are the two things. So easy, relatively easy for the quantum computer, and very hard for the supercomputer. Now let's explain what's the random quantum circuits. And basically, the Google's computer we have at that time have 53 qubits. Basically, you have all those qubits. They apply the gates, okay, randomly select those gates, apply on each of those qubits from a set of gates. Apply on that one, and these are the single qubit, and those one are the like 2 qubits. Basically, you can think about it's kind of like the unitary matrix multiply on the qubit basis, and they will repeat. Okay, you can think about one round, then random sampling another round, and they're giving the M round. Why they do the different round? Because they wanted to increase complexity, increase hardness for the classical computer to do the sampling. Okay. Now, in the end, after you apply all those gates, the quantum circuit, the qubits in this quantum computer, in these gates, you make measurements. Okay. You will get the sum of each qubit will be 1, 0, or 1. So in the end, you will get, like in this case, 53 lengths of 10 bit string. Okay, so that's supposed to get that. That's your data. Okay, so in this case, if we have a B bits, those bit string will belong to this space, length of B and 0, 1. Okay. Now, how many number of this one? It is 2 to the power of B. So exponential increase. You will see if you make this like the bigger, eventually, and make these steps like the cycles more, eventually you will make it so hard for the supercomputer to calculate, simulate this. Okay. Now for the quantum computer, what you do is you just carry out this one in the end, make a measurement, you will get the data. Okay. So it turns out these problems can be illustrated as the size biased sampling scheme in that cases. It's just in this probability space, okay, discrete probability space due to sampling. Now, what's the sampling in this case? Remember, for each realization of this randomness, you have a circuit. You can make measurements. There's a probability distribution over there, okay? And then there's another layers of, because we apply those gates random, okay? So there's another randomness. There's 2 layers of randomness there. So it's like the 2 layers of randomness. So you make the classical computation so hard because of that one. So there is idealized cases like they can make it argue that one if that depth goes to infinity, and you will approach it to so-called the asymptotics. It's the ideal part times distributions in that case. Now, what is the scheme? You can see this corresponding to, if you treat this circuit is corresponding unitary matrix on the 2b times the 2b, all those unitary matrix. It's this one, this idealized asymptotic limit sense, it corresponding to if you put a higher measure on this all of those unitary matrix, and you sample according to this higher measure, okay? And what happened is that one, each fixed sample of the qubits, unitary matrix corresponding one realization of these qubits. You make the measurements. Basically, all those qubits were in those states. So if you make the measurement, you observe any of the bit string in this space, it will correspond to the probability of the amplitude square, as I mentioned early on. The difference here, this amplitude is also random. Okay, there's another randomness there. So we'll call it random circuits. So this randomness under the idealized cases is illustrated at this point. You sample IID from exponential distribution, okay, and then you normalize this one and make this amplitude square corresponding to this probability. Okay. So what happened is that observed data is the bit stream. It's essentially the bit string, those bit string you observed according to this probability, 2 layers of probability scheme, and in these cases, okay, space. Now, as I mentioned, our qubits are not perfect. There's noise there. This is the ideal cases. You have this probability distribution according to this. Actually, there is additive noise there. So that in the real cases corresponding to this one, the model is this probability observed those strings is equal to some epsilon times the idealized probability plus 1 minus epsilon, and here we put some noise. And this one is the uniform noise on this space. Okay. So this epsilon is the fidelity, basically the measure what's the like closeness of the sampling distribution with this ideal distribution, or is it how many like the percentage of the bit streams are really from the output distribution from those carry out those circuits. Now, if you forget about all those quantumness, you can summarize in the idealized case. What's the sampling problem? The sampling problem is like the biased sampling. You have this probability space, discrete, with the cardinality equal to 2b. Okay, you have a sampling scheme. The sampling scheme is basically this all of those bit string in this space. You draw one of each of those bit string is according to this probability. Okay. Now, what's this probability is the weight of this uniform and those from the exponential, okay, carry out the probability. Okay. The issue is the B increase, okay, the real problem is the size increase as the depth increase, the simulate this board using the classical computing is so hard. Remember the classical computing, when you need a sample from something that you need to know the true distribution, okay? To find out what's the true distribution, it's very hard, so hard as you increase the B and increase M. At that time, the best supercomputer can do is about the B equal to around 50, M is about 20. Okay, beyond that one, we don't. In principle, there is a truth still, but we don't know. And in the supercomputer cannot calculate that one. Remember, the quantum computer do this sampling is relatively easy. They are not calculating the underlying true probability. They just run this process to get the sampling. Okay. So in a sense, it's the physics, okay? Now you will see that when we talk about the computing, everything is about the physics. And because we don't pay much attention, if you do the sampling and using our current computing like MCMC, basically you are using the electronic physics to do the sampling. And in these quantum cases, they're using the quantum theory to calculate, to do the sampling. So the cases here is that the sampling problems, also you push this away, it will be so hard for the classical computing, but the quantum computing is easy. You can sense that one is eventually we will get there, demonstrate that things. Similarly, for the boson sampling is using the process from the optical systems. You build up the photons pass through the beam slit and splitter and the photon sources, phase splitter. Basically, build up optical systems, and there's like photons pass through this network. At the end, the photons will be appear here and there. You find out where they are because of the randomness. The location of this, you detect the location will have random. So the random, there will have an underlying distribution, okay? And that underlying distribution, similar to the random quantum circuit, is output distribution, okay? Now, in these cases, we can write down exactly what's the output distribution. The sample space is basically you assume that the M photons and M mode. And so the state will be the M of those digits. And the only constraint is those number must be equal to the total number of N. So you can easily find out the cardinality of this one is equal to this combinatorial number. Okay. Also, remember this is the optical system is there is a unitary matrix represented on this whole system, like in the circuit cases. So there is a unitary matrix size of M times M and represented the whole system. Okay. Now, with those things, we can write down the probability, the true probability distribution. So basically, being each of those states, discrete probability is equal to this, denominator is easy, the numerator is you using this state to, from this big matrix, you got a sub matrix from this one. Then you need to calculate the permanent, okay, not a determinant. Permanent is like the determinant, except that the no signs. Minus I plus j. Here is no signs. It's just all possible summation over here. So it turns out, unlike the determinant, much easier to calculate. Permanent is the P sharp complete complexity is very hard. So essentially, it's for the quantum computer, you just run this process. You get the detect the photons. You get the sampling. But for the classical computer, in order to do the sampling, you need to calculate those probability, okay? And then according to probability, do the sampling, and calculating those probability is very, very hard. So as we increase the certain size after a certain point, and you will see the quantum computer, the classical computer won't be able to do that one. Okay, so this is the similar to the cases, it's the automation, why those sampling are easy for the quantum computer, so hard for the classical computer. Okay. Now, the one is here is you can see is as we in principle we now as we pushing we can find out the way we can move in these things to that regime that is supercomputers won't be able to handle. We said the intractable regime. Now, in that regime, we don't know what's the truth. Because we cannot calculate. Quantum computer simulate the samples. Now, how do we know? You build up a quantum device, you draw some data, okay? And how do you know this one is truly from that one, the distribution, which we won't be able to calculate? So that to demonstrate the claim of quantum supremacies, you would need statistics. Okay, again, that's a statistic that comes to play. Is the one, how do we benchmarking to prove the quantum speed up? In that case, the sample you generate from that device, indeed is from the true in target probability distribution. Now, at here, there is the issue like you have the input and you have a quantum computer with resources, you have the input from a classical computer with those resources, you get an output. Quantum cases, the output following the certain distributions. And in the classical cases, you may use the randomization, and if it's not random, and with the distributions to indicate quantum speed up. Basically, for the classical computer, you will need much more resources, like the computing time, bits, and those kind of things than the quantum computer. And then you can prove that there is a quantum speed up. Now, at here automation, how to prove these cases? We need to generate a sample. Basically, you need some kind of a benchmark, apply on those distributions, generate a result, classical quantum cases. And those are the performance on those benchmark. Two things we need to show. One is statistical efficiency, another one is the computational efficiency. What's the statistical efficiency? Remember, those quantum distributions, out distribution are grow exponentially with the size. So if you wanted to try to estimate those distributions, okay, or anything like the fancy enough for those distributions, you would need the exponential sample size to estimate those things. So the statistical efficiency we want to means we only allowed to have a polynomial sample size, what would allow us to estimate those things, because in the interactive regime, we don't know the truth. We only have the sample from quantum computer. We need to use statistics to estimate those benchmarks. Okay, and you will later on I will show that on many like usual things won't be able to have the statistical efficiency. Now, for the computational efficiency, it means we can calculate those benchmark in the polynomial time, okay, not the exponential time. So those one are the issues associated with that one. Now, in the very simple cases, in the factoring problems, you can easily say that both statistical and computational efficient. Like because it's just a prime, you put a number there, the solution is correct or not, just multiply those together, simply find out it's correct or not. And so the computational efficiency is very easy. Statistical efficiency is also easy because you estimate those probability. You don't need that. You only need a polynomial number of a sample to estimate those things. Now, in the cases of the noise quantum computer, okay, remember the one what we have, it's not the perfect quantum computer, it's noise versions, there's noise there. So we can define the similar cases, put a star here to illustrate they are the noise version of the idealized cases. There's a noise version of that one. So we need the benchmark, we need to apply the measure the noise, like the generate from noise quantum computer generate data, and the classical generated data. And again, we need to handle statistical efficiency and computational efficiency for those benchmark. Automation, if you're using the usual things, like for example, there is the distribution of this, there is the distribution, there is a true distribution, okay, and of this one. For the true, basically all of those targets, we're trying to looking for the true distribution, okay. Now, if you're using, compare this one, you're using all those distance, okay, usual distance, and it turns out there's a proof, basically using the quantum tomography and all those things, you will require exponential number of sample size to estimate those difference and estimate. So it won't be statistically efficient. And the Google, they defined a so-called cross entropy benchmark, and using some of the asymptotic, like I mentioned, that Porter-Thomas regime distribution to come up with that one to show it's a statistically efficient, only needed a polynomial sample to estimate this benchmark. Computationally, none of them are computationally efficient, is because quantum computer are not trying to calculate the underlying true distribution. The classical computer won't be able to calculate, do the sample, calculate the true distributions over the like the quantum supremacy regime, like once at that kind of intractable regime. No one knows what's the true underlying output distribution. So you can only like hope this will work. So largely it relies on the statistics. You build up using those samples, but you need to calculate the true of them, need to calculate, you need exponential number of times. So what you do, you use in the statistic data to build up statistical models and do the extrapolations and to illustrate this point. Now, whether this is cases, sure that one is still there's not enough things to research on this part. So this is one of them to illustrate that point. How much time do I have? Okay, 5 minutes already. So this is the basic scheme and to study for this one. Now, what's the result? Like the two projects, like the Google and USTC, and they showed the quantum supremacies. So basically, all of those results are the mention that they are based on circumstantial evidence, because the intractable regimes, we really don't know what's the truth. And on the other hand, we want to claim that it will happen or that happened. Okay. So basically what they do is they build up, use the engineer physics and simplify the models and collect the data and analyze what happened in the intractable regime. Okay. And then trying to infer what happened in the tractable regime, what happened in the intractable regime to see what happened there. Now, in the Google studies, they for these simplified like circles, and they collect the data sample, and they're using quite a sophisticated statistics based on 30 million of the data. And in the end, they estimate this benchmark, and it's 0.2%. What it means in that sense, the claim is about the 0.2% of the bit streams truly come from the idealized output distribution. Okay. Now, if you're using the supercomputer, okay, classical supercomputer, trying to generate bit stream with match up with at least with this kind of like the fidelities, like this much of the data come from output distributions. They illustrate that one is with the different with the 53 qubits. Okay, 53 qubits. Remember that is the state omega is the 2 to the power of 53. That big size. Okay, and with the depth 12, they were estimated 2 hours to calculate this one, and by the classical computer, and increased based on this model, statistical confidence, bootstrap, all those things. Now, in the end, the estimate at the trendies, that one the supercomputer cannot calculate what happened there. The estimate build up this model to see that one require 10,000 years to do the like the sampling and 200 a second sampling. The sample, by the way, 1 billion bit stream. Okay, and to sample 1 billion bit stream, it will take the 10,000 years by the best supercomputer at that time. Now, again, if you wanted to calculate this one, this part is the really, if you want to truly calculate, you can see the break. They didn't calculate what happened. It would take millions of more years to actually to calculate those underlying distribution. This is just the sampling. Okay. Now, once this result published, there's many immediately like the challenge refute about the claims result, and with the many ranging from the device, noise, the new algorithms come out, and the computational models, the statistical issues, the evidence, all of those things are related to that one. And so there's a lot of like the debate, discussion, and continuing for and against on both sides and about these issues. Now, for the USTC project, and they actually argued there's a 0.99% of fidelity. Basically, there's not much noise. They're trying to see that in the simplified cases or the smaller cases, they can check with against the underlying distributions and find out very fit. And then they just said, well, in the intractable regime should be work, and also the build up for the classical computing. What's the time required to sample that 200 second jobs, and basically it estimated it will be like the 0.6 billion years at the best quantum computer. Okay, now of course there's tons of like the issues and the debate, and largely it's because there existing a wide range of views about the quantum computing, ranging from the hype to the skepticism about the quantum computations. And even for these quantum supremacies, they illustrate, even just from the purely statistical point of views, you would see there's a lot of like issues to be resolved. So if we expect a long-term race between the fast, like the classical algorithms, and the improved device, so it will be continue probably until we build up a quantum computer actually can run those like short algorithms, and immediately to demonstrate that theoretically proving advantage. Maybe at that point things can be settled. Now this is just one cases. Furthermore, there's a lot of more of an interface between the statistics and the quantum computer. Remember, to build up a quantum computer, you will need like the many cases, like the quantum systems, that so many parameters, models, and you will see involve a lot of issues for building quantum computer involve the statistics. And also you build up the device, you will see how do you know the device will performance according to your design. So that the certifications based on the many issues is highly related to causal inference and in that part. So on the other hand, if we have like the quantum computers, you would see there's great potential to revolutionize many of the statistical computations and the machine learning things. Now, much more of the much beyond these statistics, there's a lot of things going on in the quantum computer. Thank you.
Any questions for Yazhen?
I really not sure that I understand. You compare quantum computer to general purpose computer, what you call classical general purpose computer. To be fair, you have to compare it to a silicon-based machine that is specially built to solve a specific problem. What would be the result then? That's a fair comparison. Otherwise, I would ask you to compare quantum computer to leaf computer, which is the best computer I know to compute the path of a leaf falling in a free air.
Yeah, that's a real fair questions, and I think that the one we are not at that stage. I think because of the at this point we have all those theory they are proved, and we just people are trying to say, can you show some things and in the real calculations? And this one again is just one of the demonstrated the concept. Maybe you can say in the statistic sense, and to show there is a cases we can compute that one. Like the things you mentioned, yes, it failed, but we are not that yet, far from there yet.
Thank you. So is there a program that people can turn every classical algorithm with quantum computer algorithm? Is there a systematic approach to do that?
Yeah, it's basically that all the classical algorithm can be treated as a quantum algorithm. And because of all those like a gate operation can be realized by the quantum gate. the real issue in the quantum computation, we are not to say that those can be fed to the quantum computation. We are looking for the fast speed. So if you can, for the certain things, if it is, because you can convert that one, if it is no fast speed, no speed up, so we don't look at that one. So we are looking for the fast, when you for the certain problem, you do the quantum ways, can compute it much faster.
So you don't know which, give you an algorithm, you cannot tell me which one is faster.
Well, the quantum computer can never be slower than the classical computer, because of the mention that all those classical algorithms can be treated as the quantum algorithm. They cannot be slower, but whether they can be fast or not is the one we are looking for.
Is it obvious it's more energy efficient?
Well, that's no. Yeah, like the cost and the energy efficient. That's another factor.
The couple of slides back, the 0.2% measure statistics that you had, would you call that good or bad?
Well, the one is remember the goal of that one is trying to have some problems. There's no practical purpose can be used to practice, just create a problem to demonstrate these concepts. Yeah.
Well, that's my question.
Yeah.
So if we restrict our attention to quantum supremacy experiments, and hopefully in the next few years, there are a couple more coming out, what do you think are the outstanding statistical questions that needs to be answered that haven't been answered so far in those papers?
I feel that even for the quantum supremacy project, like for example, there is a lot of if you trying to, let's say, using the FDA, like in the pharmaceutical company, we develop a new drug, we did a lot of statistics, you get to the FDA, need to check all those analyses. If you use that one as the golden standard, okay, probably many of those analyses won't be able to pass that standard, okay. So there's a tons of issue. I think probably there's like for example, in these problems, like in the Google study problems, and like there's a noise model for there's noise model there, right? And the quantum computer that generate the data from that noise models, and like I and we and others, they try to look at it. Does the data really feed to the model, the physical model there? Does not statistical test basically reject the hypotheses, does not feed to the model. But we don't know because there's so many complicated issues there, and we couldn't find out any suitable model to feed the data. And but on the other hand, there's so many as I mentioned the issues there. Yeah.
So are there advanced statistical tools that might be used to guess what the right form of the noise model is going to be on the global depolarized error model?
It's not I don't have a solution to that one. That's one we need more of a statistician to work in this field, and hopefully they'll resolve many of those statistical issues. Yeah, I don't have an answer to that.
So I see there are no more questions. So let's thank Yazhen again for this great talk.